right, welcome to the Thermal Energy Network Modeling Tools panel. My name is Aeowyn Kendall. I'm with Aztech Geothermal, and I will be your moderator. Today we will be hearing from, in order of appearance, Brendan Hall from CHA Solutions, Jason Willeford from Jacobs Engineering, or just Jacobs, Victor, whose last name I still don't know how to say. It's Polish. And Brian Urlaub from Salas O'Brien. So with that, I will hand it over to Brendan.
All right, thank you. So like I said, Brendan Hall with CHA Solutions. That's how I run our renewable thermal energy systems group. I'm based out of Syracuse. A lot of our group is based out of here in Albany. Unfortunately, we've moved the conference away from the parking lot next to our office, which means the commute's a little bit longer now. But it's a great spot, and it's been a great event so far. So the overall title of the session is the Thermal Energy Network Modeling Tools. I'm going to do a little bit of just kind of teeing up kind of the rest of everyone, and I'll talk a little bit about one aspect that in particular. I said I have the obligatory log rolling slide where I have to mention things and do a plug for the ASHRAE Building Energy Modeling Professional. I've done ASHRAE for a long time. It is a certification that ASHRAE has that is meant to kind of show expertise in building energy modeling. It's a recertified certification, and so always good to mention that when it's relevant. And also, like, we have two webinars that we have done for Design Builder, which is a graphical front end for Energy Plus that's specific to how to apply that particular program to the design of ground source heat pumps. And also there was another one we talked about optimizing that for a series of kind of ECMs. So we're talking about trying to model these types of networks. There's a range of different options, and it depends very greatly on what you're trying to accomplish and what stage of the project that you're at. So I grouped these into 4 general buckets. So you have your initial, site selection, scoping, feasibility type tools. Those are where you're just, it's almost urban planning at that point, where you're trying to decide where these things make sense. You're looking at the characteristics of the community, the building, the state, the territory that you're trying to work in. You bring it down one level, you're talking about modeling the energy use at a building level or maybe a series of buildings. And so that's kind of one class of tools. Those are your classic energy modeling tools with, Energy Plus or Train Trace or eQuest. You get a little bit further into kind of the component level, and that's where you're talking about the purpose-built ground heat exchanger design programs that are doing the physics of what's going on in the ground in a very detailed kind of way. Then you kind of tie everything together and you get into what Victor and Brian will get into is like kind of the urban scale modeling, where we're doing very complex modeling that are trying to capture what all the different interactions are. And so, it's trying to find, not all tools are meant for each point in the process. So, trying to find, what's the question you're trying to ask, what's the best tool to answer that question, and not getting too detailed too early, but also, trying to capture enough information to where the answers that you're getting are going to be useful throughout your project life cycle there. So yeah, the scoping tools you're looking, it's a lot of very high level data collection, site selection, and master planning. I kind of went over the other aspects of the other buckets of modeling tools. So digging in a little bit more into kind of scoping and feasibility tools. And this is where, there is a lot. I mean, you might have noticed in some of the other presentations, there's a lot of further development. There's, a lot of people are trying different things to do what a lot of people are doing kind of in-house right now. A lot of what is going on is still happening in like very custom tools. Either that's, spreadsheet based, or we're doing a little bit more now with kind of GIS type tools where we're trying to estimate loads on a really large scale and like an urban scale, aggregating those in different ways that is also flexible. We can look at different combinations, coming up with, things like scoring rubrics and weighting scales to try to automate and put some numbers to what combinations make sense and where we value those different attributes. And then also, obviously, the finances are such a big component of this, and trying to come up with what combinations of things create a viable project. And so the financial models are obviously very important with that. And those are, lend themselves to a spreadsheet. We are doing a lot more with GIS tools. So this is an example of a sample ArcGIS. It's a heat map of just building area, which, we have some other ones that kind of have different proxies for building area in heating loads and cooling loads. And when you start layering those data sets, a lot of these are publicly available data sets too. You're layering those things on, you're looking at environmental justice areas, you're looking at BOAs, you're looking at things where either things that maybe help projects financially, like brownfield, you might have a tax credit with it, or things like overmapping the gas system of a utility, where you're looking at, hey, where are projects that might be at the end of their existing system or just beyond where their existing system is. So maybe there's a project that would avoid having to extend that system. Anything that might lend itself to where there's multiple beneficial aspects that exist in the same geographic space, and where there's density. I know so much of the economics of this is based on density proximity. And so that's where there are a few kind of purpose-built commercial tools. A lot of those focus on automating the data collection, data visualization, cost estimating, and economic analysis. A couple of those examples of things that we've used for different times. There's a program called MPro. That's a web-based app that is out of the UK. There's a company out of Denmark called Comsoft. It was originally built for building out fiber optic networks that they adapted to district heating systems. That's an ArcGIS plugin. But a lot of these tools are a product of the markets they're in. So a lot of the tools are meant for the European market, because if you've ever looked at a map of how many district heating systems there are, say in Central Europe, Denmark is definitely a prime example. They're all over the place in a way that you probably don't even realize until you see one of those maps. So a lot of the tools are just meant for that market. So it's been a little bit of a challenge of trying to adapt those, especially with things like converting from metric to English. So, and obviously if you're doing something in Canada, then you don't have to worry about that. But a lot of the tools are coming out of that market. So they do tend to have the characteristics that are kind of unique to those markets. And then we talked a little about kind of the data sources we're pulling from. There's a lot of stuff we can do with things like property tax records. Most municipalities have kind of GIS formats now of the property tax records, and those generally have things like building square footage. It's usually to build the space usage type in a very general sense, but there's challenges with that. A lot of them, the formatting is not consistent. There's not a uniform way to do that. So then trying to do something where you have a tool that works over multiple municipalities, but the field is named something slightly differently, and so there's some data processing you have to do to clean that up and make it useful. Depending on where you are, there's economic development organizations that might have data sets that you can pull from, as far as especially large buildings. Obviously we do a lot of field surveys, utility bills to try to reconcile things that might be unique to a certain area. And then DOE reference building sets, which I'll get to in a second here. The EIA is obviously kind of a reasonable, authoritative source for information. Their forecasts are sort of famously bad, but as far as a authoritative source, look up solar implementation sometime of their estimates. But as far as a authoritative source, same thing. NIST has this really good life cycle analysis guidelines that have things like, here are utility escalation rates that you can use. Now, if what's happening with natural gas prices 5 years from now, there's probably a much more profitable job you could find doing some trading there. But it's at least an authoritative source that you can say, hey, we can all sort of agree that this is a reasonable approximation. And then, real quick, a little bit about the DOE prototype building set. So these are building reference sets that were developed by the DOE. They're maintained by Pacific Northwest Lab. They're standardized models. There's 16 different building types, covers about 70% of the commercial building stock type across all the climate zones. And so they update these every time there's a new code cycle. And because one of the things they use these for is, say, when there's a new version of 90.1, they go through, they say, here's the buildings. Here we make all the updates for the energy code based on different space types, different system types, and then they aggregate everything together. They weight it by the building stock in the United States, and they'll say, 90.1 2022 is 5% more efficient. And so we as the DOE recommend that states adopt it. And so that's how they come up with that number, is through this data set. So there are, yes, like I said, 16 different types. They have spreadsheets that go into actually a lot of detail into what all goes into those. It's the envelope, it's what the HVAC system. They're all basically based on 90.1 Appendix G guidelines. It's all code minimums for the envelopes and all the things like lighting and plug loads, and they have usage patterns that are based off of research that have been done in those different types of areas. So they said that the custom versus commercial tools, there's always like this balance between trying to do something that is going to automate something versus how much time it took to put the tool together. And so we're still very much, I think, on the bespoke to projects. I think things are moving in the other direction as more projects progress and as these things become more common. The same thing as the commercial tools, I think, will come. This is one example of like an Emerald development platform that is meant to help develop these tools. It's open source. There's a lot of research. There's a couple of researchers that we're working with that are hopefully going to be able to work with all this data we're getting from these U10 projects to help kind of move some of these tools forward. And so, people are aware this is a problem. And so there are tools in the development. And so, when we're talking with this 5 years from now, hopefully we'll be talking about a whole different set of tools that are very much meant to do these, and it's going to make everyone's life a little bit easier. So, all right.
All right. Thank you, Aeowyn. Good afternoon. My name is Jason Willeford. I work with Jacobs. Jacobs may not be much of a household name in this market just yet, but we're a pretty large company. We're about 45,000 people across the world, doing all sorts of cool things in different sectors. But we've been doing district thermal energy for decades for now. But about 2 years ago, we stood up all of our energy and power resources as a global business unit with a singular purpose of decarbonizing energy. So that's what gets us pretty excited about TENS and geothermal, and that's why we're all here. So I'm going to talk a bit about master planning before turning it over to some more detailed design conversations. Master planning can be pretty complex, but it's an important part of the process. So plans can take all sorts of different formats. It could be a feasibility study. You can call it a decarbonization plan, an energy transition plan. But if done right, it can help you sell the whole story, right? It's an expensive endeavor to start going into thermal energy networks and geothermal exchange. And it's not always the lowest life cycle cost, but often it can be proven to be so. So planning is important. So how do you do that well? Utilities infrastructure is complicated, right? If you're dealing with existing infrastructure, there's a lot of it. It's buried, it's aging, it's probably not super well documented. And depending on how big of the picture you're looking at, whether it's just the geothermal loop or if it's all the way back to on-site and off-site power, if it's the building side of things, that scope can get pretty big. On top of that, another layer of complexity is stakeholder engagement. So this is really important. Of course, it's an important part of the process. You want your plans to have the ability to capture that level of complexity, all of those details without losing the important details, but to enable you to model things out with enough simplicity that you can move quickly. We all have to deal with limited timelines, schedules, budgets. Of course, we don't have infinite money and time. So we need to cover a lot of ground in a short period. Our way of doing that is a software we developed in Python called Virtual Infrastructure, or VI. So the whole idea here is to make something dynamic, data-driven, help us take all these great ideas, get them on paper, do the math, crunch the numbers. But on top of that, we want to be able to let the people using the software do so quickly. We want to be able to brainstorm a whole lot of options with our stakeholders, start to pare that down as quickly as possible to the most viable options, and then dive into more and more detail and really get into kind of an early conceptual design as we get down to our preferred option. It's got to be data-driven, and ultimately it's got to be able to cross over many engineering disciplines, right? We don't want to be just limited to the mechanical engineers working in one silo, electrical in another, but also in addition to that, we want to be able to tell the story to the non-technical folks, or the folks that are the management types, or the people that are making the decisions with how they're spending their money. There's a whole lot of priorities that you're going to come up with as you talk to your stakeholders, whether internal or external, but here's a few of the more important ones that recur on these types of projects for us. So obviously reliability is key. Your infrastructure is critical. It's got to be resilient. It doesn't have much time for downtime or any sort of outages or interruptions. In addition to that, though, we don't want to just look at how it looks at the end of the process. This is usually a multi-year process of build out. So we want to make sure that we're maintaining the right level of reliability throughout the build out. Sustainability is the imperative. I mean, that's why we're here. We like to be able to try to capture what the existing facility looks like today and what its energy use, water usage is, carbon emissions, you name it, and then track what that looks like as we ramp that down over the years. We also want to keep an eye on how we're ramping up our electrical demands, of course, and making sure that we have the right infrastructure to support that. And then, of course, expenses, right? We can't avoid that expenses is the bottom line. But we want to make sure that the story is focused on the life cycle costs, not just the upfront capital costs. So upfront costs matter, of course, and that's enough to derail a lot of projects. But we want to really keep the light on how low the operating costs are for systems like this so that we can show just how low the life cycle costs of these systems are. There's a whole lot of capabilities. I'm not going to read the list, but our goal with this software that we wrote was to try to bring as many capabilities into one umbrella or one software as we could. We wanted to be able to make a change anywhere in our plan and have that propagate throughout, because we don't want to spend a lot of time, dealing with cross-discipline interfaces and updating multiple models. Again, we're still at a planning level, and we want to be able to cover a lot of ground. We want to look at a whole lot of options, and we want to be able to do so as quickly as possible. All right, so let's dive into the details of what we're actually doing. So it all starts with the building energy modeling. You can do that in a couple different softwares, like was mentioned. We like to do it within the same software. We built it originally on eQuest and moving more towards Energy Plus, but there's a whole lot of different ways you can do your building energy modeling. Once you aggregate all those cooling and heating demands and put those out on one graph, what I really like to do, what we like to do with our teams is to plot out a given year and just demonstrate where the opportunities are with those overlaid cooling and heating loads. We like to overlay a couple other things too, like outdoor air temperature, wet bulb, dry bulb. That can come in handy when you're talking about hybridized systems. Set points. I think set points and setbacks are a good thing to demonstrate on these curves, and that can shine a light on a few areas where you can drive some efficiencies in your system design. And then when you get to the level of knowing your thermal energy network temperature drift, overlaying that as well can be very helpful. You want to take your baseline heating and cooling that's simultaneous and just take that right off the table and serve it with this simultaneously heating and cooling equipment. But you also are now starting to look at your balanced heating and cooling consumption throughout the year and looking at how far those offsets are time-wise, and that helps us inform just how big that geothermal field is going to be and what that's going to look like. Then a lot of systems that we're looking into hybridizing them. So the excess cooling, the excess heating demand, that's where we're going to start figuring out where are we getting that extra energy from or where are we dumping it to. We do flow modeling within the software as well. You can do it pipe flow, Fathom, whatever works for you, but we like to build it out here because, again, with this software is built out year by year so that we can just draw out on a map and understand where the disturbances are going to be for our utilities or our clients, and just help understand where that resiliency is going to be maintained each year. If we need loop systems or mesh networks or what have you. And then finally, we get to the equipment operation and sequencing. So we're pulling the real-world equipment performance data and we're putting it into the software and we're checking out, are we not just operating within the equipment capability, but also how efficiently are we running the equipment we've selected. So this can feed into, better equipment selections, better basis of design equipment as early as practical, because that's going to drive a lot of the cost of the project as you get farther into detailed design. And then, of course, I'm mechanical, so we usually gloss over the electrical. I'll probably breeze through this side, but ultimately we need the electrical infrastructure too. The whole purpose of VI and really any good master plan is to be cross-discipline. So we'll build out substation increases, expansions and duct banks and whatever else we need to make sure that we're powering our equipment. But that's just one of the disciplines that we load into the software. We can run everything from telecoms to potable water, sanitary sewer, storm, you name it. And then finally, I'll just quickly mention, one case study. So we've deployed this at a number of campuses. Kind of our niche is typically like universities, national labs, federal research centers, campuses that own all the utilities and have that infrastructure. And this is just a piece of the puzzle. So we've had good success with this in recent years. And the case study I'll point out is University of Georgia. If you were at IDEA in February, you probably heard a presentation about that. But the neat thing about this one was we looked at everything for them, right? We looked at everything from business as usual, which was maintaining existing gas-fired boilers for a central steam plant, serving the whole campus, to decentralized chill water plants that were all in separate systems that weren't interconnected, and then a whole bunch of options between that extreme and the extreme of cross-connecting the entire 60,000 person campus on one thermal energy network, with a few geothermal bore fields and some waste heat recovery from sanitary sewer. The neat thing was, not only was it like a light bulb moment for the stakeholders and a way that we accomplished everybody's different priorities, but ultimately over a 30-year planning window, we were able to find that we were saving them tens, if not hundreds of millions of dollars from a life cycle cost perspective. So that's the importance of planning. I'll kick it over to Victor next to talk about detailed design.
Good. Hi, everybody. My name is Victor, and we get progressively more detailed on this side of the table, so get ready.
Good.
My presentation is network modeling tools, and then enter the Moderator universe. So I'm at SmithGroup, and I'm on our impact team, and I do things like this. Anyone else have really cool Halloween costumes? I saw one hand, so it's a small group. This is my one-man rock band, Geo Rocks. Anyway, look out for that coming to a music venue near you. So the impact team at SmithGroup looks at not just building scale, but campus scale. So I'm a senior engineer there. And we're here talking about more of the campus scale stuff, but it all plays a role. So for district energy modeling, we've set the stage a little bit already with this, but you take historical or energy modeling loads, whether from publicly accessible data sets or custom bespoke energy models, and then you pick your district modeling platform. So we saw a couple of those already. And then you look at the results. So maybe you're looking at scenario planning, infrastructure planning, energy use, cost, emissions, and then I'll even touch on some of the use cases for controls, making sure this is going to work correctly, or maybe controls optimization or validation before you install and troubleshoot in the commissioning phase. So one of the things that we do in the early stage process, can you see the cursor? No, but on the bottom left, we show that energy modeling for the year, so hourly values. On the right, it's going to be aggregated. Just as okay. Hourly values that we heard earlier, and then this is aggregated for the year. And then what you'll see is that we can bring different buildings online at different years and then scenario plan out based off of the different technologies we can deploy. So maybe you want to, useful idea is stacking technology. So do we have potential for heat recovery? Maybe we have wastewater in certain buildings or campuses, and then add in geothermal, stack that, look out at a certain year and look at the infrastructure cost or the required thermal demand that needs to be met. So this is kind of one of the high level tools that we use. Oh, it didn't work. And then you might ask, so what about complex plant designs? What about controls testing? What about this ambient loop thing that we're hearing about? So if you aggregate loads and do detailed modeling, that's a certain type of style of analysis. But what if you want more accuracy? So this is where we enter the Metallica universe. So there's, Brian's going to probably have a different take on this, but this is our take. So a little background on Metallica modeling. Has anyone heard of Metallica before? Okay, well, again, we have one hand for costume and one hand for Metallica maybe. So small group. So it's not something that's unique to building infrastructure, building design, district analysis. It does have great capability in that space, but it's being used in aerospace, robotics, very different markets. And it's a Gen Z. So it's relatively new to the game, so it's more modern in some of the analysis capability it has that's been built relative to some of the other older tool sets. It's even newer than Energy Plus or Transys. Some of the other details of it, it's object-oriented, so if you see a component, you can use that component to build any custom network that you want or system that you want. So you see a heat pump, you can connect it to a pump, you can connect those to a bore field. So it makes it a little bit intuitive to assign these networks. It's acausal, so that's a technical way of saying you don't need to tell it which way the flow is going to go in a pipe. So you could have it going one way or another way. You can solve based off that, which is important in ambient loop designs. It's multi-domain, so you don't have to set it up just for mechanical simulation or just hydraulic simulation. Some tools are just specialized in one thing. You can look at mechanical plus electrical plus controls. This diagram shows, hydrogen, other types of networks. If you're layering them on each other, a lot of flexibility there. So let's start to compare like a traditional energy modeling versus Modelica modeling. One of the takeaways you have when you get started in it, it's kind of like bowling without bumpers a little bit. It's maybe a little bit, there's a lot of flexibility, which is great because, you can be as creative as you want to be as an engineer. But it's a little bit different from traditional energy modeling that if you, it's more of a direct, usually there's some bumpers, there's maybe some process to follow. Some of the comparisons here, I would say traditional energy modeling is more for building loads. This is could be used for single building plant design or district design. It doesn't do the individual building loads very well. It can do it, and there's methods for it. But it's great for multi-domain analysis. Like I mentioned, it's great for advanced controls. There's some real life control one-to-one applications where you can deploy the controls directly to a building. So there's some really great opportunities. So let's meet the Modelica family. So Modelica in itself is a modeling language, and there's multiple environments you could use to access this. So Model.Impact, Dymola are both proprietary type. You pay a license to access. And then there's a big push to make this accessible to the masses. So Open Modelica is an option to access Modelica modeling. And then, let's do something with that modeling environment, and that's dependent on the libraries that are built out. So there's open source libraries and proprietary libraries. So that gives you those components that you can then assemble into a system. So one of the paths that we use is Model.Impact for the modeling environment. And then the benefit there is that gives you access to both some of the best open source and proprietary models to combine when we build our systems out. So what is Model.Impact? Well, it's one difference than most software is it's not a local installation, it's cloud-based. See, there's ease of collaboration. We can send links to each other, collaborate on the same models. We can deploy that to clients. You can set up dashboards with this advanced modeling setup. You could do rapid simulation with parallel simulation of multiple cases. And they include libraries and support, which you wouldn't get with open source. So the modeling interface, you assemble the systems, you parameterize the systems on the right, but it also can be a coding interface. So you can use Python natively in that environment to code and test your system models. The buildings library has 2,000 validated open source components. So if, that's available no matter what environment you want to go with. And that's developed by the Department of Energy Lawrence Berkeley Lab. So amazing stuff there. And everyone's got to have a favorite Modelica model. So mine obviously is the Borefield model, which acts kind of like a physics nesting doll. So you can deploy this model, you connect it to your piping network. Under the hood, it's actually a series of one YouTube, and all the physics are built on that. And what you get is a short-term and long-term response. There's no need to use a third-party software to then develop that response. You could do it within the software. A lot of software doesn't let you do short-term and long-term response. Short-term would mean like managing electrical demand charges and peak loads. And you can also do long-term seasonal imbalance like you do with traditional sizing software. I mentioned digital control delivery and managing risk and controls. There is work done now to take this model and deploy it directly to a building automation system. So if you're a building owner and you want to de-risk your complex plant design, you could bypass all the commissioning and controls vendors, directly deploy it to your BAS. Really powerful stuff. Another thing is you have worldwide resources for development. So I'm part of the BIPSA working group. A BIPSA working group is a simulation community of 300 of the top researchers around the world that are developing this or features for this. So instead of picking one developer and then you really want to feature develop, but they're not prioritizing it, you have access to all of these different research communities to pull from. One example is maybe there's a 4-pipe heat pump that can do heating and cooling. You want to deploy a 6-pipe that could do heating, cooling, or simultaneous. You take that model, copy it, tweak it, and then redeploy it. all within a modeling environment. You don't have to get down to a code level. So as an example of an ambient loop that could be created in that, here's a series of buildings that are cooling would be rejecting heat, heating, extracting heat. There's a bore field in there. And then you can even do pipe to ground heat transfer of that distribution network. And you could have a pump with real controls, like a PID loop control on it. So if you run it, you can visualize temperature. So as you extract heat, you can see the loop getting cooler or the loop getting warmer as you reject heat to it. You can run these annual simulations to really drill down into the what's happening in the model to get transparency on it. And you can look at any point in this and extract any result that you want, temperature, power, anything. Thank you.
Good afternoon. Well, I'm not as fun as Victor. I should have had some, interesting slide of a Halloween costume. I think I was Eddie from Christmas Vacation in my last costume. That would have been fun. And the robe, maybe not appropriate for this audience. But anyway, Victor had a really great presentation. My presentation, not quite as fancy with the really nice graphics and so forth. But Transys, and I'm going to talk a little bit about Transys, which is a transient dynamic modeling software tool that we've been using at Salas O'Brien for about 6 or 7 years. We started using it as a company primarily for central plant design, and then used it to design our first thermal energy network, which was the Braciszewski project up in Toronto. And the reason why we went to Transys at that time was because we couldn't find any other tools out there that really could model that particular system as a holistic system, not each individual component, individually, but as a system. And so we started working with this group out of Madison, Wisconsin, and they've got this Transys program, which Transys in the past has primarily been an academic software tool. A lot of thesis papers and master degree students, use Transys for thermal modeling of all different kinds of, studies. And it wasn't really utilized in engineering environment for the most part. It has been recently, and I think we're probably one of the few firms, but I know there's others that are using it now for more actual engineering work. And what we found is that Transys is really basically building a digital twin. So we're really putting together basically the pumps, wires, and pipes as you would in real world. You would go build it. We build it in a software platform. And similar to Modelica, you can operate that, and you're operating it and being able to look at any point in the system on 15-second intervals and see how the system is operating. And then you can optimize from there by changing control sequences and dispatch models. So the tool's got a tremendous history in academia. Again, coming into the engineering world, it's found that it's highly complicated, very difficult, not user-friendly software. When you talk to engineers that get into it for the first time, they find it very cumbersome. The other issue is it doesn't give you any wrong. It won't tell you if you have a wrong answer. It'll run the model regardless of whatever you put into it. And so you really have to kind of understand what you're looking at, the outputs, and like you said, there's really no guardrails to it. You can get off the rail pretty quickly. And so somebody with some experience has to be able to look at it and understand if it's right or not. Thankfully, those people at TESS are with Salas O'Brien now, so we have them kind of guiding our engineers, making sure they're looking at what we're putting together for our clients. But again, it's a parameters plus inputs, software that gives you outputs. It's got a lot of modules similar to Modelica. There's thousands of different modules that are built into the open source portion of Transys. I shouldn't say open source. It's a subscription service. Geothermal being a big one, and the geothermal model in Transys is highly dynamic. It's very flexible. It isn't a static, rectangular bore field. You can design it and build it as it's actually going to be designed and built or built in the real world. So the geometric shape, if it's inclined, if it's vertical, all your different soil properties, all the things that go into geothermal design, it's really critical. So you can plug all those numbers in, which is really important for what we use it for, which is almost all of our geothermal projects, whether it's campus and central plant type work or utility thermal energy network type work. So again, it's really putting together an interconnected, complex system and all of its components, and you write control sequences to get it to operate, just as you would if you had a building and a BMS system, and you've got to write code to be able to get it to operate. And the nice thing about this digital twin is then, as similar to Modelica, you can output that exact same operation sequence, put it on the plan and spec, and now the building operator has exactly the code to write to operate the system how it did in the model. The other really interesting thing that we're doing with Transys is then after a year or two of operations, we'll take all the data collection, we'll go back in and retune the model to exactly how it's operating after the first couple of years. And now we can predict further out into the future how it's really operating and if anything needs to be changed, added, or subtracted in the future. For instance, we've got a project in Wisconsin that is a very large geothermal system, one of the largest in North America, and they wanted to put in thousands more boreholes, and they didn't know when they needed this. They're going to add 40 more buildings to their campus. So we built the digital twin, plugged in all their data from over the last 10 years, tuned it to that data, and then optimized and looked at, okay, well, if you change this or you add this building here, you're going to need another 500 boreholes 5 years from now as your temperature creep starts to happen or whatever. So it's great for predicting, future events. And then you can also do a lot of things similar again to Modelica when you talk about rate structures and really optimizing dispatch models based on what you're paying for your utility rates, which can be really helpful, especially in the central plant world. You can put in a lot of thermal storage and do things that you can show, well, if we charge this at night on off-peak, versus doing it during the day on peak, we can save thousands or hundreds of thousands of dollars in utilities every month, which was one of I think Princeton won the award here last year for commercial top job. Maybe it was last year before. But at Princeton's tire plant that we designed and using Transys, they thought they needed another 1,000 boreholes on that campus. We went in and ran 3 different dispatch models and showed them you could skip the 1,000 boreholes and just dispatch your thermal storage tanks differently, and it saved them approximately $80 million. So they were fairly happy with that output from Transys, rather than putting in all these boreholes. So, it's very dynamic in that way, but again, it takes quite a user that's had some experience with this to really be able to get into it, understand it, and know what they're looking for. Otherwise, like I said, you can get off the rails, and there's nothing that's going to stop you from getting off the rails and having the wrong output that everybody's relying on for the design. Okay, and this is just basically how you build the pipes and wires. This is very similar to Modelica. I think Modelica's got much better user interface. I think it's probably a lot more intuitive when it comes to building these systems. This is all built pretty much one component at a time. So all those little shapes are different modules. So the ground loop module, you click in, put in all your data, every pump, every wire, all the electrical data, all the building loads, everything's got to get put into here. And then you've got to basically write the sequence of operation on how you want it to operate. And so it is building a digital twin, but a very cumbersome way to do it, but it gives fantastic outputs if you do it correctly. And with thermal energy networks, it's really important. I think we've kind of seen how, number one, especially with single pipe systems, what's the temperature profile of that loop? How does each customer get impacted by temperature change across that loop? Is everybody being treated equally? Or are people on the end of the line, getting kind of the short end of the stick with efficiencies? What is that efficiency degradation? Is it severe, or is it not a big deal and we don't really need to worry about it? Or where do you plug in those energy resources into that system to keep everything within that balance? Okay. And then again, how does each building interact with the loop and share energy in those shoulder seasons? If you have a heavy cooling dominant building, showing how all that works together. And then of course, with your geothermal systems, showing, again, how you dispatch that, the long-term net effects. The great thing about this program is I can actually separate all those bore fields, where all the other programs generally put the bores into one model or location, which doesn't then give you the correct output of the drift or the how it impacts over the long term. right? And we need to model that. And that's one of the beautiful designs inherently about thermal energy networks and having distributed resources. You have them spread out so they have more land in order to get energy or put energy in. And so they don't get impacted as much as if I had a campus with 600 bores all on one field. That's a much different design. And there's a different thermodynamics happening within the ground on that scenario than if I had, 50 bores in 10 different locations. So that's what this really does for you on that level in modeling, which, again, it's dynamic. It can really show you all those things. And it's, again, building that digital twin. And these are just some of the, graphs and so forth. But I'll say this, Modelica has a much better graphical interface, user interface. This all has to get outputted basically in either like a spreadsheet format, 8760 format, however you want to view it, and then you've got to build the graphs. It doesn't have any type of a graphical interface, which is, too bad, but that's not what its primary function is. Its primary function is to run calculations. And again, it's primarily built for academia so that it, somebody else does all that other interface work. So, it has its pros and cons. It's, but it is a really good software for modeling, I think, thermal energy networks, specifically geothermal. The other really interesting thing about the program is you can plug in any other type of thermal asset. Like right now, we've got a project where we've got boreholes, a river solution, sewage heat recovery. Well, how do those all interplay with one another? Because you have much different temperature profiles throughout the year. So when you look at what a ground loop is doing in the middle of winter versus what a river might do or a sewage, it's completely different temperature profile. So how do you dispatch that properly? Are you actually able to use certain assets at certain times of the year, or are they counterintuitive to the other asset? Right? Like the river might be 80 degrees in the middle of summer, my bore field might only be 70. Why would I run the river system if my bore field is colder, giving better efficiency? So you have to really understand all of those things and be able to put them together in a system, look at it holistically and how it all interacts. And if you can't do that, I think it's really hard to model other ways and really get a true picture of what's happening. And then the best part is you can actually help your clients really build operational control sequences so they know what to do when they start it. Because if you don't give them that with these types of systems, if they've never done it, they don't know what to do. And we're seeing this across the board in a lot of situations. So that's one of the really great things about, Transys and that modeling tool. So thank you very much.
All right, we will take some questions from the audience at this time. So go ahead and hit them with what you've got.
My name is Hendricks with Will Dan Incorporated. And I made a few notes real quick. Let's see. It was Brian when I was in college, and we did all that stuff manually. And then next semester, we learned the software. He asked the professor, what the? He said, you got to know what's going in and what's going out. So garbage in, garbage out. So I like that. But basically with Jason, you mentioned CapEx, capital expenditures, and I heard utility rates from Brian. So the core of my question is, you have fiscal budgets or annual budgets, and you're designing a long term. So price-wise, going in and out, does that take into account that can change? Right? And you're designing stuff that's going out 20, 30 years. So those systems can adapt to that information?
Yeah, I'll start. Y'all can hear me? We apply just a basic inflation, and historically our inflation rates were pretty good and pretty stable. Last 5-10 years, I would say maybe that's not so accurate anymore. Who can predict the 8-10% inflation in given years or whatever? So maybe that answers your question. Or we're definitely applying inflation year over year for infrastructure as it's being built out.
That's key. Thank you. Yeah, that's it. I forgot about inflation adjusted. And now we have tariffs, so it's a new layer of uncertainty, I guess.
Yeah, I'll just mention real quick about Transys. Transys isn't an economic tool. Transys will give you the consumption peaks, all that data that you've got to put into some other tool to get economic analysis. So Transys is really just giving you all the energy data, and then you've got to take that and then, further put that into whatever, whether it's spreadsheet or any other type of modeling tool for economics. So yeah, just wanted to clear that.
Mike Kingsley with Ramble. Brian, following up on that, but does the system know the utility costs or the emissions, or so you can dispatch, say, based on lowest emissions or lowest fuel cost?
Yes, correct. You can plug that in and certainly run your dispatch models based on either rate structures or emissions, however you want to look at it. It just, you could put dollars and cents to it and get the annual, utility total costs and so forth, but we just generally don't use Transys for that. But we'll use it for dispatch modeling, yeah.
Yeah, hello. You could do the same thing in Modelica space, and even because something like Impact is cloud native, you could even look at real-time emissions. For example, Marsville emissions from watt time. That's a resource that we've used. So you can start to run dispatch models based off that or whatever you're interested in.
Does either Transys or Modelica have optimization capabilities? It sounded like you had to prescribe pipe properties, pipe diameters, wires. Do you have to optimize yourself by hand every piece and put it together, or can it search the solution space to come up with design recommendations?
And the question asker is?
Marshall Pondrelli with McPhail.
Thank you.
Again, yeah, that's one of the downsides of Transys. You have to really analyze the outputs and then as an engineer make, those optimizations and then go back in and change the program and rerun it to see if your intuitions are correct. So it does not have any type of optimization programming within it. You have to make those manual changes and then rerun the program, which, on large systems takes a lot of time because every time you might hit one run simulation, it could take 4 to 5 days to get an output. So, yeah, time consuming for optimization.
I'm not judging. I was just curious.
Yep.
I could answer for that from my take on the Modelica side. The Modelica modeling language, so modeling environment is important. So, you could run optimizations with Python on your Modelica model, but you still, there's no easy button approach right now. There's room for development, I would say, for optimizations. That's what UrbanOpt, Brendan mentioned that early on. NREL talked about, maybe you want to mention that, but UrbanOpt is developed for something like that, for, conceptual use district planning. But I do say there's some caution there, like what Brian said, on, the first time you put a system together, it's going to take troubleshooting. Even the controls are so real that if you respond too quickly, the solver can't solve. It's too dynamic or something, right? So it takes troubleshooting. Once it's set up, you can start to explore that space and maybe run some optimization on it.
Yeah. Connor from GeoFees. Two-part question for Jason from Jacobs. What was the business case and market potential that you're seeing to develop in-house district geothermal energy modeling software? And when did you make this decision, and has that business case changed recently?
So that tool was initially stood up around just master planning. The business case was kind of easy at the time. This was probably 4 or 5 years ago we started developing it. We were doing it in Excel. So the difference between Excel and Python was, and getting really to the point where we were asking Excel to do too much, was kind of the business case. So it was a bit of an easy decision from there, and I think it's paid dividends. We've done probably 4 or 5 projects just in the last year or 2 that have been heavily based on virtual infrastructure. Not a small undertaking, so yeah, the budget of funding that was important. But we do have an innovation fund, so we kind of have internal competition, so to speak, to apply for innovation funding, and that helped to spur that along. And then I think you had a second part of the question, sir.
You said you made this decision 4 years ago, but has that business case changed recently?
No, I would say we're leaning even more heavily into it. We're taking it much further. Not to give away all our secrets, but we're building upon this software that's currently really geared towards master planning. to go much deeper into more detailed design. So I think we can go pretty well into like a schematic or conceptual design level, I would say, with virtual infrastructure. But, doing detailed designs and following that through construction is really our niche. So, we're building upon it and going a bit further.
Brandon, I believe you wanted to say something more about Urbanout.
Yeah, so I'm just going to add on that with the optimization. So I know there are kind of R&D academic type level stuff going on. For some systems, if you have a small system that's, say, like a single bore field that's doing like 4 or 5 buildings, you can simplify that down to like a building model. And within that, so for example, like one of the things we had done with Design Builder, which is out of the UK, like they have an optimization tool built in there is where you define a number of different options. You kind of give it some cost parameters for those different options, and it'll go through an optimization process either for different goals, whether it be carbon or energy, or you can give it a couple other goals. But if you have a small enough system where you can simplify it down to, some district systems are from a square footage standpoint are smaller than some large buildings. So there are instances where you can do it on that. But yeah, once you get above a certain scale, you definitely need one of these other tools.
Any other questions? We are on time. Yeah. Well, I do actually have one fun question. Victor, can you say your last name?
I like the way that you did it, so I gotta want to have everyone be creative with it. No, it's, if you want to know, it's Braciszewski, so Victor, Braciszewski.
All right. All right. Let's thank our panelists.